Hi, I'm Siti Aisha and I'm going to present about Bernoulli's theorem. Bernoulli's principle stated that as speed of fluid increases, pressure decreases. For a steady flow, the amount of fluid entering the pipe must be equal the amount of fluid leaving the pipe. So, the fluid speed in the thin part must be increased. Here, if you see in the diagram, the air in the wide part has a higher static pressure than in the thin part. Assumptions involved in deriving Bernoulli's equation along a streamline are steady flow, incompressible fluid, and friction by viscous force must be negligible. Here is the Bernoulli's equation. Bernoulli's equation between 2 points is this one. Objective of this experiment is to investigate the validity of Bernoulli's equation when applied to the steady flow of water in a tapered duct. Second, to measure flow rates and both static and total pressure heads in a rigid convergent and divergent tube of known geometry for a range of steady flow rates. Apparatus and equipment. First, we need the F110 hydraulic bench. Second, we need F115 Bernoulli's apparatus test equipment. And lastly, a stopwatch. Here are the methodology for equipment setup. For methodology in taking a set of results, first, the pressure difference H1 to H5 is set to be 50 ml using air bleed screw. After the specific volume of H1 to H5 is reached, the ball valve is closed and the time taken to accumulate 3 liters of fluid in tank is measured. Next, step 1 and 2 are repeated with a different level of H1 to H5, which are 100 ml and 150 ml. Then the test section is reversed to get the diverging flow. The test section is removed by unscrewing the two couplings and being reversed. The couplings are tightened, and lastly, step 1 until 3 are repeated for diverging section. Here are the results for convergent flow. Total head for convergent flow is calculated to be decreased from H1 to H5 for all pressure difference. In the other word, we can say that H1 is the highest and H5 is the lowest. Meanwhile, divergent flow is the opposite. Here are the results for divergent flow. For both convergent and divergent flow, velocity increased when fluid flow from wider to narrower area. And also, be it convergent or divergent flow, velocity increased as pressure difference increased. So, as velocity increase, dynamic head calculated will also increase. Note that divergent flow from pressure head H5 to H1, which is from narrower to wider. However, after the experiment, there are some errors on the results shown in the divergent flow, as it shows some raise and also drop of total heat from H1 to H5. As an example, if you look here, there is a drop and then a raise. You can also look at here and also here. This situation might due to some error or weaknesses when taking the measurement of each data. One of them is the observer must have not read the level of static head properly, where the eyes are not perpendicular to the water level of the manometer. Therefore, there are some minor effects on the calculations due to the errors. Here is the sample of calculations using 50 mm. For conclusion, first, we can say that Bernoulli's theorem is valid. Next, in a narrower area, fluid flow in high velocity. Total heat in convergent flow decreases from H1 to H5, but total heat for divergent flow increases from H1 to H5. Then, all the flow rates and both static and total pressure heads in a rigid convergent and divergent tube are managed to be calculated. And lastly, from the Bernoulli's equation, we can say that increase in velocity will result in drop of pressure. That's all from me. Thank you.